Let's go through a few examples now that show how maximum entropy models behave, and in particular we see how maximum entropy models don't double count features in the same way that the naive Bayes models did. So for these examples, we're assuming this teeny empirical data set here, so that there are two features, each of which can have two values. So there's little or big B and there's little or big A, and we've got this distribution of the 6 data points. And so these are the features that we're going to put in our models. So the first feature is to say that we have a probability distribution. And so once we put in that feature, the maximum entropy model is to say, okay, give a quarter of the probability to each outcome. Now the second constraint we're going to put in the model is that we're going to say, well, but wait a minute, there are a lot of big A's in this data. So our second feature is this red feature. And the expectation of that red feature in the empirical data is 2/3. So we add a parameter to the model that captures that. And so then the distribution that we get is that 2/3 of the data has to be in this column. And so each of these cells is then uniformly 1/3, 1/3. Well, suppose what happens is we just add a second feature to the model, which is actually looking at exactly the same thing and saying that the expectation of getting a big A must be 2/3. Well, we now have two parameter weights, lambda prime and lambda double prime, but what we're going to optimize the model to do is to say, well, the sum of the expectations in this column must be 2/3. And so what is going to happen actually is that the sum of lambda prime and lambda double prime is going to be the same as the value of the old lambda A, and we get exactly the same probability distribution right here. The effect of that in maximum entropy models is that features that duplicate the evidence of other features tend to not get much weight. So here's an example from our named entity model. So what we're doing is predicting the named entity that goes on the next token here. So we're tagging along a word at a time, and we're doing at Grace Road, and we've said that at is other, and we're going to want to give named entity tag to Grace. And our two candidates in these examples are person or location. So you could reasonably think that Grace is the word Grace is a good indicator of something being a person and should therefore have a high weight for person. And if you look what's actually in the model, well, it does have a positive vote right here for Grace being a person, but it's a fairly weak positive vote. And a lot of the reason why it's a weak positive vote is actually just knowing that a word starts with G is actually a rather strong indicator that something is a person. And so the current word feature is a special case of this more general feature that the beginning of the word starts with G. And so most of the weight goes to there, and there's only a little bit of positive weight on knowing what the current word is. Okay, now let's look at a more interesting example where we have features that overlap but aren't exactly the same. So this time, here's our empirical data that we want to model these 3 points of empirical data. So as before, we start off by constraining the values to probabilities, and then as before, we put in this red feature whose expectation is still 2/3 in the empirical data, and so that gives us the same distribution as before with the same parameter weight lambda A. Okay, but what now if we want to add an extra constraint to our model to capture the fact that there's data over here? Well, the obvious thing to do is to notice that capital B also has an expectation of 2/3 in the observed data. So let's add in a feature that's true if a data point has a capital B, and let's add that to our model with a weight of lambda B. You might be hopeful that that would mean that we model the data perfectly, but actually we don't. The maximum entropy distribution is this one here, where we get 1/9 chance of little b, little a, so we've smoothed the model a little, which is maybe good, but we don't get a uniform distribution over the other points. We get weights of 2/9 in these two cells, and 4/9 in this cell. So you're expecting almost half the probability mass to go to getting big A, big B. If you think about in terms of the parameter weights down here, it's kind of obvious what's happening. That for the case of big A, big B, both of our features fire, and so the weight that goes into the Maxent formulation is the sum of lambda A and lambda B, and therefore its probability has to be much higher than the probabilities that are assigned to just lambda A and lambda B alone. Now there's no weight over here, so you might have thought that that should still be getting probability 0, but remember that we do have to be observing the empirical expectations of the model. So the constraints of our model are that the probabilities here should sum to 2/3, and the probabilities here should sum to 2/3. And then we've added in this constraint that the probability of this cell should be double the probability of this cell. And if you work through those constraints, the maximum likelihood solution is precisely the one that's shown here with 4/9, 2/9, 2/9, and 1/9. So what that shows is that maximum entropy models don't model for free what statisticians call interaction terms. That if we want to say something special about how the combination of having big A and big B behaves, we have to do that by putting in extra features that model that. So here we have the same data as before, and we start off with the same two features as before. One way we can fix our distribution is that we can add in a third feature, which is true if both A and B are capitalized. Well, the expectation of that feature in the observed data is 1/3. And so that feature then determines that the probability of this cell must be 1/3. Well, given our other feature constraints coming off these other columns here and here, then what we get is that the probabilities are 1/3 in each cell, and we exactly model the empirical distribution, including, of course, now that we do get probability 0 for the remaining cell. I mean, of course, that's not the only way that this could have been achieved. We could have instead assigned a different feature, F4, which is true in any of the situations of A, big A, big B, big A, little b, or little a, big B. So in any of those three situations, it has the value 1 and 0 otherwise. And we can make a model with this feature alone, and it would also give exactly the right distribution. So in general, the thing to take away from here is that a lot of the time we want to put in features that model interaction terms or that model sets of data. I mean, in particular in natural language contexts, commonly what you want is to have features that model natural classes. So something like a feature for the character is a digit, or the character is uppercase, or the character is the letter E, regardless of whether lowercase or uppercase. That those kind of natural classes make good features because they'll cause the model to generalize in good ways. How, though, do we find out which features we want to put in our model? So inside statistics, when you're looking at logistic regression models, and maximum entropy models are basically equivalent to multi-class logistic regression models, what it's standard to do is to do a greedy stepwise search over the space of all possible interaction terms. I mean, that is, you don't evaluate every possible subset of features because that number of possible subsets of features is exponential, but you start with a null model and you one by one add in the feature that is the most useful out of all of the features that aren't yet in the model until you find a good model. That works reasonably well in traditional statistics cases where you have maybe 10 or 20 features. But for the kind of cases that we do in natural language processing, we commonly use templates to generate thousands and thousands of features. So for instance, if we just have a what is the current word feature, that's a feature that might have 50,000 values over a typical training set. But we don't only want that feature, we want features like what is the previous word, what is the next word, and often we want higher order features like what is the word pair of the previous word and the current word. So very commonly we get models with millions of features, and indeed it's those models with millions of features that optimize the performance of our system. And well, if we have millions of features, we just can't be affording to train millions upon millions of models to try and work out what's the roughly optimal set of features, even doing it in a greedy fashion. And so therefore in NLP it's actually normal that which features are put into the model and which interaction terms are put into the model is just being determined by hand based on linguistic intuitions. Not always. There has been some work that has been looking at automatic ways to find good feature interactions, though even that work is having to do some fairly heuristic things to make up for the fact that the search space is so big in this case. Now here's an example showing feature interactions at work. Here we have again this same example with at Grace Road, and so we have what is the previous class, and so in our example the previous class was other. And so what this says is that if the previous class was other, it's very unlikely that the next word is a named entity. Those are strongly negatively weighted features. And that's just really because most words aren't named entities, and if you've just seen what you came before you wasn't a named entity, probably the next word isn't a named entity either. On the other hand, if you see a word that is capitalized, so this is done by these word shape signature features, so it's a capitalized word. Well, capitalized words in English are just normally proper nouns, and proper nouns are normally entities. So that then this feature has very positive weights for both person and location. Okay, so those two features are banging against each other, and if you add up those terms, well, certainly in this case just the sum of those weights is approximately 0, and so you're not actually getting any particular evidence that a capitalized word after something of class other is going to be a named entity. But that's just wrong, and so to get the model to work better, what we have to do is put in an interaction term that models the conjunction of the previous state being other and it being a capitalized word. And then when we do that, we find that this interaction term votes quite strongly for either for the word being either a person or a location. When features overlap, it's actually quite subtle the way the weighting of the features works, but it's something that's important to get a sense of to understand how Maxent models work, and I hope these examples have helped with that.